Hey everybody, here's the notes for the fourth section of Unit 4. And this is about the Pythagorean theorem, which I know that you've seen before. We talked about this with distance. But we're going to talk about some Pythagorean inequalities too today, which is maybe something new for you. All right, in every right triangle, the square of the hypotenuse is equal to the sum of the square of the legs. So the idea of the Pythagorean theorem in words can be a little confusing, but when you look at it, it really is a very simple relationship between this side here, which is our hypotenuse, your longest side of any right triangle, the side that's opposite that right angle, is called the hypotenuse. And that right angle in this box means that this is guaranteed to be 90 degrees. So the side opposite that right angle has that longest relationship. And then we have our two legs, whether we have a short leg and long leg, or you can even have an isosceles right triangle. Either way, each of these two legs is going to represent the two sides that are including that 90-degree angle. So the measure of c squared is equal to a squared plus b squared. So there's lots of proofs out there of the Pythagorean theorem, and the one that we see the most is a picture that looks like this. And I want to make sure you understand what it is that it means. So if I have side B here, and I can say that this has a length of 3, 1, 2, 3 units. If I were to square this, I know that 3 squared is equal to 9. So this area here, 3 times 3, is equal to 9. When I talk about my A side, this classic right triangle is what we call a 3, 4, 5 triangle, because if this is 3, and we make this 4, when I square 4, 4 times 4 is 16, and that's going to give me these 16 triangles, and I can count them, or know that 4 by 4 is equal to 16, the same as 3 by 3 is equal to 9. If this third side of my triangle has a measure of 5, 1, 2, 3, 4, 5, that 5 squared is going to fill up an area of 25 square units. Now what's interesting here is my 3 by 3 gives me 1, 2, 3, 4, 5, 6, 7, 8, 9 units. So these orange are represented by my 3 by 3, and these 16, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. These 16 from my 4 by 4 square perfectly complete this 5 by 5 square that I get from this last side. So this relationship is pretty cool. A squared plus b squared is always going to equal to c squared in any right triangle. Now here's some fun facts about the Pythagorean theorem. There are other proofs of the Pythagorean theorem. Some are in geometric form, spatially, and some are in algebraic form. So they're fun to look at for sure. See if you can figure out which U.S. president discovered his own proof of the Pythagorean theorem. So if you can answer that for me next class, that would be a real feather in your cap and a gold star for sure. Here's something I bet you that you didn't know, and this is crazy, continuing our theory of plagiarism. Pythagoras didn't actually discover this truth. So he learned it from the ancient Egyptians. Pythagoras was a philosopher and a thinker. He liked to explore patterns. What he did figure out is the Pythagorean triples, and we're going to dive into that a little bit later. But Pythagorean triples are any time that you have whole number values for all three triangle sides. And by whole numbers, I mean no fractions. Remember, our rational numbers are our a over b's, and our irrational are typically anytime you take the square root of a number. It's not a perfect square. So we'll talk more about Pythagorean triples at a later date. When we talk about the converse of the Pythagorean theorem, understanding that we can say if this relationship is true between those, or if it's 90-degree angle, then I have this true relationship. The converse is going to turn those two conversations around, telling me that if this relationship between the sides is true, then we can go ahead and say that that side opposite that longest side is a 90-degree angle. So this is how we can prove a triangle is a right triangle. And that's going to be that converse again, which is going to be the opposite of what we are initially given. We're given that if it's a right triangle, then this relationship is true. And the converse is going to switch that around. If the relationship is true, then I have a right triangle. So in your warm-up, you ended up looking at whether or not we can classify any of these by what angles they have. And we said definitively no. We needed some kind of rule that can help us do that. And that's what's coming up next, to understand what kind of rule will make that true. And what we're going to do is talk about these as Pythagorean inequalities. So if you have a relationship between a and b squared that's not equal to c squared, we can dive one level deeper and figure out if maybe our triangle is acute or if maybe it's obtuse. And it helps us if we think about it as compared to c. So if c squared is smaller, and you can see here that this distance, if triangle ABC were a right triangle, and if we had a right angle there, C would need to be longer in order for it to be a right triangle. Because C is smaller, and we'll make sure that we understand C squared is smaller, because it's smaller than that distance it would take for it to be a right angle, we know then that this triangle is going to be acute. If that c squared is bigger than it would be. So let's go ahead and give ourselves a right angle here to make this a little bit more accurate. And then we can see here, if c squared were equal, it would be a right angle. If c squared is bigger, that must mean that this angle opens up wider, which makes this triangle an obtuse triangle. So if c squared is smaller, it's going to be acute. If c squared is larger, then we're going to end up with that obtuse triangle. So we can use that Pythagorean relationship to not only prove it's a right triangle, but we can also talk about whether it's acute or obtuse. Okay, so first of all, let's talk about how we go ahead and solve for that missing side. Our side C is always going to be opposite of our right angle. So I know that 20 squared is going to be equal to my 15 squared plus my x squared. So when I go ahead and I solve this, I can set my equation up, and like I said, it's easier if c is over here. So 400 is equal to 15 squared is 225 plus x squared. So when I do some subtraction, I get 275 is equal to x squared. Now we look up here and we were asked to leave our values as simplified radicals. So because they asked for that, finding the value from the calculator is not going to be what we need to do. But I am just going to check Oops, that's not what I want to do. I am just going to check my math real quick. And I know that is, oh, there we go, is 175. And I know that if I go to take the square root of 175, I know that that's going to give me an irrational number with decimals that never end. So I don't get a whole value, which, by the way, tells us this is not a Pythagorean triple. So what I need to do when I solve this is take the square root of each side. So I know that x is going to be equal to the square root of 175. I need to think about 175 in terms of perfect squares. And I know that 25 goes into it. And I can use my calculator again 7 times, which means that I can take the square root of this perfect square. So my x value is going to be equal to 5 times the square root of 7, because this 25 can come out of the radical. So is it a Pythagorean triple? No. So which is the right triangle above have values that represent Pythagorean triples? Not number 1, that's for sure. Okay, let's take a look at B. I know, again, here is my right angle. So here is my hypotenuse. And I know then that x squared is going to be equal to a squared plus 12 squared. So we'll go ahead and do that math. X squared is equal to 64 plus 1, 44. And we can go ahead, 64 plus 1, 44 is going to be equal to 208. So x squared is equal to 208. And I know that's not a perfect square. I can prove that. Taking the square root, and again, I get an irrational number, a number that I can only round to estimate, which means I need to figure out how to go ahead and simplify this radical. So when I look at 208, I know a 4 goes into it, and I know that goes in 52 times. And I know that 4 also goes into 52 again, 13 times. So because I have this double factor, I can pull that out of the radical. So x is equal to the square root of 208. This double factor can come out of the radical sign. So 4 can come out, and square root of 13 stays in. And again, is it a Pythagorean triple? No, it's not, because I don't have a whole number value here. Let's go ahead and check out C. My right angle is opposite of my hypotenuse. So I know that 21 squared has to be equal to 10 squared plus x squared. And I can solve for x. 21 squared is 441 is equal to 100 plus x squared. So 341 is equal to x squared. Take the square root of each side. The square root of 341, guess what? Strike 3 for me. So x is going to be equal to the square root of 341. Now here's a trick for you. If you want to find the factors of 341, you can enter in the inverse variation, go to the table of values, and look down and see if any perfect squares are factors. Because 341 is made up of 11 and 31, those are all prime. So there's no way I can simplify that value. So the square root of 341 is as good as this one gets. So which of the triangles above have Values that represent Pythagorean triples, none of them. Because what we need is 3 whole values. All right, last part. Determine whether each triangle is right, acute, or obtuse. Notice we don't have any boxes here, so the best I can go with is saying that this has got to be my longest side. And I look at my values, and I know that 4 times the square root of 35. Oops. I know that that's bigger than 20, so I do know that this is my longest side. Don't always trust the picture. Check the numbers and the math before you decide which is your longest side, because you need to make sure that you get that hypotenuse right. All right, so this is what we're checking. Is this a right triangle? If it is a right triangle, then 4 times the square root of 35, and this whole quantity squared. And we're going to look at the relationship between that and 20 squared and 13 squared. We're going to look at the relationship of 89 squared, and we're going to compare that to 80 squared and 39 squared. So what we're talking about here is looking at whether these are equal, greater than, or less than, so we can make a decision about what kind of triangle this is. So we'll get our calculator, and 89 squared is equal to 7,921. 80 squared plus 39 squared is equal to, oh, check it out, 7,921. So guess what? Because these two values are equal, then we can say yes. So yes, this is a right triangle. And by the way, it is also a Pythagorean triple, because I have 39, 89, and 80 are all whole values. So this is a right triangle and a Pythagorean triple. So that was a good one. All right, let's check out this one. So I need 4 times the square root of 35, and I need that squared. Now, check it out. My calculator knew that even though this was irrational, it knew to call this 560, and I'm comparing that to 400 plus 169 is 13 squared. So just in case we're checking, 20 squared is 400, 13 squared is 169. When I add them together, 569. Uh-oh. When I talk about 560 and I'm comparing that to 569, guess what? C squared is smaller. So because C squared is smaller, therefore my triangle is acute. It's an acute little triangle. So is it a right triangle? No, it's not. It's acute. All right, we got one more to go. And we'll talk about these side lengths here. And again, I want to find my largest side length. So how about 52 squared? And we compare that to 28 squared plus 4 root 2 squared. So 52 squared is equal to 2,704. And I'm comparing that to 28 squared, which is 784, plus 4 times the square root of 2 squared gives me 32. Now here's something I want you to stop and think about. There's a huge difference between these two. So 32 plus 784. If I'm comparing 2,704 with 816, it's obvious this is much bigger. But it's so much bigger, it makes me wonder, is this even a triangle? So what I need to do here is go back to that other lesson and think about, is the sum of my two smaller sides bigger than this side? When I add 28 plus 4 times the square root of 2, I don't even get 50. And I need 52. So we're tempted to say this is an obtuse triangle, but guess what? We got a problem here because this one is not even a triangle because of this relationship up here. So when we're doing these, we need to make sure that if you get an answer of obtuse, you want to make sure, first of all, is it even a triangle? All right, good job on these. Make sure you do your homework and come to class with questions.